let's continue our discussion. In the last video, we have discussed an example. Here it is, example 5.8. And this example was quite simple. You can see we have solved it, and then we have got some value of maximum x here, 2 meter. And one thing here, g has been taken to be 10 meter per square second to keep the calculation simple. Okay, so instead of 9.8 meter per square second, g we have chosen here to be 10 meter per square second. Now moving to the next example, which is 5.9, and it is related to the previous one. What is it saying? Consider example 5.8 taking the coefficient of friction mu to be 0.5. Okay, now they have introduced friction, and now we have to calculate the maximum compression of the spring. So let me redraw it. Here you have spring, and here you have a car, and this car is moving with certain velocity and collides with this spring, and there is some compression. There is some maximum compression up to where this spring gets compression. So in previous case, there was no friction mentioned. So the only thing was the total kinetic energy of this car is going to give rise to the potential energy in this spring. Here, there are two factors. One, the compression of the spring, and another, friction. So this car is not going to compress the spring as much it could have done in the previous case, because there is a dissipating force here which is going to reduce its energy. So that force, friction, should be, we know friction is mu times mu, maybe mu s or mu k. Here mu is mu k, that is coefficient of kinetic friction, times normal. Yeah, mu k, because this car is moving and there is friction between the two surfaces which are in relative motion. So this force will also contribute here, and work done by this force, friction force, let's say F, a small f r. So work done by this force will be force times displacement. And here, let's say, once again, maximum displacement we are denoting by xm, but this xm is different from the previous one. So this much work done is going to reduce, means friction is doing this much work done, that is going to reduce the car's energy, and then the compression will be less compared to the previous case. So how much it should be? Let me write it. Minus kxm square by 2 equals to 1 by 2 m v square, where v is velocity of moving car and then m is mass of the car. Now, it was in the previous case. Now we have to do one thing here, and we have to subtract the amount of work which is done by the friction force. So we have to write here mu k and into n, that is mg. Look, new normal, n is normal. So normal is nothing but a counter force for balancing this gravitational pull on the car. So this is equal to mg, because there is no vertical acceleration in this car. There is no vertical acceleration, net acceleration, we can say. So these two forces should be equal in magnitude. That's why here we have written, instead of n, we have written mg. Now we can rearrange these terms, and then we will have something. Look, one more thing here. This is potential, this is work done by the spring force. So potential energy rise should be negative of this work done, that is k xm square by 2 equals to 1 by 2 m v square minus mu k into mg. Now we can rearrange these terms, and yeah, this is a friction force only, so we have to multiply this friction force with x maximum to get the work done by the friction force. So here we have to write it as we have discussed earlier, that work done should be force times the maximum displacement. So now this thing is complete, and you can rearrange the terms, and you will have k m square plus 2 mu k mg xm and minus m v square equals to 0. And you have a quadratic equation now. So you can solve this quadratic equation and you can get it here. Xm should be something. And remember, you will get two different values of xm. So you have to consider only the accepted one. So one value here you are getting maybe contradicting the things, or maybe that value will not be compatible with the problem, real physical problem here. So you have to keep the value which is suitable here. You will get two, because here you have quadratic equations. So obviously you are going to get two different values for xm. So you have to choose the value wisely here. Now, moving to the next topic, and yeah, let me write its answer here directly, and you can solve by yourself. All the things have been given here, like spring constant is given in the example 5.8, mu k is given in the same example 5.9 here, and m is also given. G you can take 10 for simplicity, and m is given, and v, initial velocity or velocity with which the car is colliding, is also given. So everything is given, and you will get a quadratic equation where you have to solve for xn. And I guess this xm should be, and this xm is 1.35 meter. Solve this by yourself. Okay, now moving to the next topic. Not exactly topic. Let me put some comments here. Okay, number one, we can see here, when we are using these concepts, we are not mentioning time explicitly here. So while doing the problems with work energy and this kind of examples, we are not using time explicitly. So no need to use time explicitly. I think right. Maybe you can check it. Okay, this is one thing. When we work on Newton's law of motion, we need to mention time. And here, when we are using this work energy theorem and all, we are not mentioning time. So this is a kind of benefit of working on work energy theorem. Second thing, we have seen we can categorize forces into two different kinds. One, conservative forces, and another, non-conservative forces. So conservative forces are those where uh, there is total work done 0 in a round trip. This means the work done is independent of the path taken. But in case of non-conservative force, this work done is path dependent. For example, if you have lifted a body to some height, and then you bring it back to the same height, and now if someone asks what is the total work done by the gravitational force, so if there is no change in height of this body from the ground, the total work done by gravitational force is 0. So the gravitational force is a kind of conservative force. But with the same thing, let's say you have moved a block from point A to B, and then you have moved the block from B to A, so that it completes the round trip. And now someone asks, what is the work done by friction force? So this is not 0. This is going to be add up. From here to here, friction force has done some work, and in the same way, from here to here, the friction force is doing some work, and this is going to be add up to give total work done. So this way, non-conservative forces are not one who are working path independent. Okay, moving to the next point. This is very important concept here. Look, we are free to choose the reference of potential energy. You can choose anywhere the potential energy to be 0. And if that selection simplifies your problem, this is well and good. So accordingly, we used to choose. Like I'm giving an example here. Like in this case of a spring mass system, we have chosen potential energy of this system to be zero at the point of equilibrium, where not equilibrium means where the spring is at its natural length, neither compressed nor elongated. So, of course, if you think, okay, I'm not going to choose Vx 0 here, rather I will choose the potential energy to be 0 at its extreme point. This is the semi spring at its extreme point. So you can choose it, but this will make your problem complicated. When you go for working, when you go for solving numericals, this will make complicated, but you are free to choose. And then throughout discussion, you have to stick with this chosen reference. So this way you can choose anywhere the potential energy, because potential energy is a kind of relative thing. So rather we are going to say that potential energy at this point is something, we better say that difference of potential energies between these 2 points is something. This will give you more sense. That's why we are free to choose. Okay. Later on, we will discuss it about more. And yes, of course, during the course, we will encounter several times this term potential energy, and you will gain the concept why we are free to choose and how it helps while working with this kind of problems. Okay. Now moving to the next point. Next topic is, I think, power. Okay. Before moving to the next point, let me deduce a very useful relation here. So if there are two types of forces here, one is conservative force and another is non-conservative force. So we can say that we can write the work energy theorem as the total force and times the displacement, let's say delta x, change in position, should be equal to change in kinetic energy. Remember, we have already discussed these things. That is, work done on a system is going to change its kinetic energy, and that kinetic energy is numerically equal to the work done on the system. So this conservative force, look here, plus this non-conservative force times equals to delta k. And we know that negative of work done by conservative force is change it means rise in potential energy. So we can write here that this Fc times delta x should be minus delta V, which is change in potential energy, plus F and conservative force Fmc delta x equals to delta k. And then we will have F non-conservative times delta x equals to delta k plus delta V. And you know, in mechanical system, delta k plus delta V is change in kinetic energy plus change in potential energy is change in total energy. Or you can write F non-conservative times delta x equals to change in total energy. As we have seen already that in case of a system experiencing conservative forces only, the total mechanical energy remains unchanged. So if there is any change in its total energy, there must be some non-conservative force acting on the system. Like in the previous example, this non-conservative force is friction force. Otherwise, the total mechanical energy is not going to be changed. Okay, now moving to the next point, power. So power is a rate of doing work. So in simple, change in work per unit time. Or you can write, this is on average, work done per unit time. You can write its SI unit. It should be joule per second, or simply we call it watt. Okay. Now you can make it instantaneous also. Like if this delta T is very, very small, instant, delta W by delta T, within this limit, we say it, this is dW by dt. Okay. Further, we can write this work done is F dot ds, where ds is infinitesimal change in position, a very, very small displacement. And then you can write it as power equals to d F dot dx by dt. Or you can write it, look, for very, very small displacement, we can consider this force to be constant. So we can take it out from this differentiation sign, and then we can write ds square dot product by dt. And then you will have power equals to, we know ds by dt is nothing but velocity. So in simple, if force is acting along the direction of velocity, this power will be simply f times velocity. But if there is some angle, we will have to solve it accordingly. That is dot product f v cos theta. Okay. So one more thing. What should be the dimension of power? This should be work done per unit time, or from here also, from any one of the equations we can get it. So what is the dimensional formula for force? This is, I guess you all know, ml t to the power minus 2, and for velocity, L t inverse. Or now you can say, so this way. Okay. One thing, what is SI unit of power? Okay, but there is some other things also. Let's say, you know, horsepower, 1 HP. We used to hear this thing. Mostly, we used to see this thing in vehicles also, where instead of HP, we use BHP, brake horsepower. This 1 HP is 746 watt. Initially, the power of a machine was to be compared with the power of a horse. So, in general, it came out to be that one horse has power equal to 746 watt. And next, oh, these are things, history things you can, if you are interested much, you can study these things on different. Okay, now moving to the next point. You have heard about the power, electricity consumption. Like someone says, okay, how many units of electricity have been consumed? So if we say that 1 unit, simply. So consumption of one unit of electricity, what does it mean? How much work done has been taken out from this device which we are using, or the electronic gadget which we are using? So to define 1 unit in terms of electrical power consumption, we have to know that if 1 kilowatt device runs for an hour, runs for uh, the power consumed is said to be 1 minute. In terms of joule, you can write 1 kilowatt is nothing but 1000 watt, and hour is nothing but 3600 second. So in terms of joule, that is watt second, you can write 3.6 into 10 to the power 6 joule. So if you have consumed this much energy, your electricity meter is going to rise by 1 unit. Electricity meter reading. Yes. Okay. Now, at the end, one example, and then remaining things we will discuss in the next video. And the remaining thing is nothing but collisions. So let me write this example for you, and then we will start it. Okay, here we have the example, and yes, what is the question here? An elevator can carry a maximum load of 1800 kg. So let's say elevator plus passenger means total force. Sorry, total force we can calculate from here. So total force acting on elevator will be This force equals to mass times acceleration due to gravity and plus this friction also there. So let's say how much the gravitational force will be acting on the elevator. This one is 1800 times, let's say g equals to 10 plus friction is 4000 newtons. So in total, this much force is acting on the elevator, and then what will be 1800 times 10, 13,000 for 22,000. Okay, this much force is acting on the elevator, and then elevator is moving with a constant speed of 2 meter per second. So velocity is 2 meter per second. Now we have to find out what is power. So power is force times velocity. Then we have 2200, and look here. You may think that okay, this force is acting on the elevator downward. This force, which is against its velocity. If it is going upward, which is against its velocity. So you can think, okay, why shouldn't we write negative any of these two terms? Force times velocity should be negative, but no. This force is acting on the elevator, but elevator motor has to exactly apply this much force in the same direction to the direction of velocity. So in fact, the force applied like the motor on the elevator is this much and along the velocity. Okay, so not to be confused, this force is acting downward, but to counter this force and keeping the elevator in constant motion, the motor has to do um, apply the same force, same amount of force in the direction of velocity. Okay, that's why I have written positive here. This times this. This is power in, look, these are all in SI system, so it should be in watt. So to write it in horsepower, what you need to do, 1 horsepower is 746 watt. Only thing you need to do is to divide this much by 746, and you will get the result in horsepower. Okay. So I guess you can do it by yourself. So this is all for this class, and now see you in the next.